Hello class, welcome to the continuation of our discussion. So recollection of our topic on the rectilinear motion. Alright, so this is our second problem, sample problem number 2. So here's the problem. A particle moves along the x-axis with an initial velocity vx equal to 50 feet per second at the origin when t is equal to 0. For the first 4 seconds, it has no acceleration, and thereafter it is acted on by a retarding force which gives it a constant acceleration ax or a sub x equal to minus 10 feet per second squared. Calculate the velocity of and the coordinate of the particle for the condition of t equal to 8 seconds and t equal to 12 seconds. Okay, so these are the conditions. T equal to 8 seconds and t equal to 12 seconds. And find the maximum positive x coordinate reached by the particle. Okay, so maximum positive x coordinate reached by the particle. Okay, so here's the solution. So the velocity of a particle after 4 seconds is computed from this. Now we use the formula that the relationship that acceleration is just the derivative of the velocity. Derivative of the velocity with respect to time. So from this equation or from this relationship, so if you cross multiply dt, so we have a dt. So cross multiplying dt, so we have a dt equal to dv. Okay, and then just changing the position. What is left, put it on the right. What is on the right, put it on the left. And then integrating both sides, so we have this. Okay, so for v, so we have here the given vx equal to 50 feet per second. Okay, at this time t equal to 0. Okay, so our limit here is from 50 to vx. All right. Okay, so integrating, so we get vx is equal to, so after substituting the limit, then we get vx is equal to 90 minus 10 feet, uh, 10t feet per second. So this is our equation for vx. Now after doing the integration here, all right, and it is plotted as shown. No, it is plotted as shown here. So here at t equal to 0, we already have the velocity vx here, velocity vx, that is already 50. Now at t equal to 0, so this horizontal axis here is that is for the time, that is in seconds. Okay, so at t equal to 0, we have already the vx that is at 50, no, given here, 50 feet per second. Okay, so time equal to 0. Okay, at the specified times, the velocities are given as follows. So t at t equal to 8, we're given here at t equal to 8 seconds. All right, then substituting it here, no, from this resulting equation after integration. All right, so substituting t equal to 8 seconds. So substituting t here equal to 8, then we got 10 feet per second. and at t equal to 12 seconds, so we have here Vx, again from this equation. So 90 minus 10 times t is 12 seconds. So we get here negative 30 feet per second. Okay? So the x-coordinate of the particle at any time greater than 4 seconds. So this is our time equal to 4 seconds. At any time greater than 4 seconds is the distance traveled during the first 4 seconds. Plus, okay, so we have here plus the distance traveled after the discontinuity in acceleration occurred. Okay, so here. So we have here a constant acceleration when there was discontinuity. All right. So we have here the result. No, uh, we have to make use of this because we are going to solve for the x coordinate of the particle. So maximum positive x coordinate. So it means that we have to solve for the uh, displacement. All right. So from this equation, we have from the formula, we have the velocity. The velocity is equal to the derivative of the displacement, right? The derivative of displacement as with respect to t, and then when you cross multiply dt, so we have v times uh, dt equal to ds. All right, and then interchanging their position, put what is left to the right and what is on the right, put it on the left, and then integrate both sides. So this one here. So integrating both sides. Okay. Okay. So we have this, and since s represent displacement, so you can use x here instead of s. So after integrating, so the limit here, we know the limit. Okay, so we have 4 to t. So after 4 to t, okay, because our it's variable, right? So this part here is variable up to this. Okay, so 4 to t, that is our limit for t, because we integrate this with respect to time. All right, and substituting, so this becomes so when you integrate this one, we have 50 times 4, right, plus the integral of this one. So after combining everything, so we get this minus 50t squared plus 90t minus 80 feet. All right, so I'm just rewriting it here. Okay, now for two specified times, so this is our new equation class with using the other condition. So for the two specified times, we have t equal to 8 seconds. So we can solve for x here, substituting the value for t from this resulting uh, expression for the displacement, that is x, which is equal to this one. So 50 times 4, meaning this area here. We're talking of this area. So the area here is just, we have here this 50. This is a rectangle. So to find the area of this one, because this area under the curve. So 50 times 4, that is this one, this part. Then plus the integral of. So this one is no longer constant acceleration. So we have to make use of the concept that we have discussed earlier. All right, so we have to do the integration here. So our limit here is, this is our at t equal to 0, meaning at t equal to 4. So this is our initial time to calculate our distance here. All right, t, this is the lower limit. Our upper limit is in terms of t. So it can be at any time t, at any point on this line, on this curve. All right, so we have generalized this one. So after integrating, after combining similar terms, so we got this our x is equal to this one, minus 50 t squared. Okay, so substituting it here, so we get a t equal to 8 seconds. Substituting, we got 320 feet. All right, at t equal to 12 seconds, so we have x equal to 280 feet. So the x coordinate for t equal to 12 seconds is less than, as you can see here, is less. So this is our observation class, is less than that for t equal to 8 seconds. So the reason is that since the motion is in the negative x direction after 9 seconds. So you see here, after 9 seconds, this is at 9 seconds here. This is 9 seconds here. After this one, it becomes negative. It goes down. All right, so that's why we got here a value that is less than. Even though the time is greater than, this time here is greater than t equal to 8 seconds, but still the result here is less than this, because this part here already goes down, negative. So the maximum x, or the maximum positive x coordinate, is then the value of x for t equal to 9 seconds. All right, so only at t equal to 9 seconds here. So after that, so this is the maximum x. So x max is using the same equation here for our x. So use the value of time before it goes negative, that is 9, at 9. So substituting, so we get here 325 feet. Okay, so I hope it's clear, class, and I hope you learn something from this. So these displacements are seen to be the net positive areas under the curve VT graph. Okay, so this is our curve VT. V, V as a function of time, but we use here Vx, so Vx sub t as a function of time, so with respect to t. All right. Okay, so that's it for this example, and I'll show you another video for the next example. So thank you for listening. Hope to see you again in the next video. So bye.